Okay, today we're going to look at how to draw force diagrams. So in our first example, we have an object lies motionless. So we start with our dot. We have gravity pulling the object downward. Okay, we can label that F and little g. And then because it's resting on a surface, we know we have the normal force, F, and then little capital N, pointing upward. Okay. Second example, we have object slides at a constant speed without friction. So again, we start with our dot. Okay. We have gravity coming downward. And then we have a normal force because again, he's on a surface. And notice the length of this arrow and the length of this arrow are the same size. Same thing happens in these because these are balanced, right? In this case, there's no arrow right or left because the object is sliding at a constant speed. So there's no friction slowing it down, and there's no force that's keeping it moving. Horizontally, it's following Newton's first law, an object in motion will remain in motion. And this, number 3, it's the same as number 2. We have gravity down, and we have the normal force up. But in this case, we also have kinetic friction, which opposes motion and is parallel to the surface, pushing it backwards. Okay? Okay, number 4. Okay, one thing to notice about this one, notice those arrows are unbalanced. There's more on the left than there is on the right, which shows that we're going to have a net force moving to the left, which shows we're going to have some acceleration moving toward the left, which is why he's slowing down. Okay, in this case, he slides without friction. Okay, so we have gravity coming downward. Now, because the surface is at an angle like this, that means our normal force, which is always perpendicular to the surface, is going to come off at an angle. Okay, I need to make this arrow a little bit longer. So there's a net force moving. You know, the right side forces are bigger than there are no left side forces. So an object is going to be moving to the left in the to the right in this situation. Okay. Static friction prevents sliding. So again, it's the same thing as number 4, where we've got gravity pulling it down, and we've got our normal force pulling it up. But now we also have friction, and again, friction is going to be parallel to the surface. It's not very parallel. Parallel to the surface, opposing motion. So it's going to come backwards up the ramp. Normal force goes perpendicular to the ramp, and friction kind of goes upwards against the ramp. Here we have an object suspended from the ceiling, so we have gravity downward. Now there's no surface that this thing is resting on, so instead we have the rope pulling it up, and we call that force tension. Okay. Now we have gravity pulling it downward. And then we have two tensions, one going this way and the other going this way, because tensions always go in the same direction as the rope. One more time, we've got gravity pulling it down. We've got our first tension pulling it perfectly sideways, and our other tension pulling it up at this angle. Okay. Now, one more time, we've got gravity pulling it straight down. We've got our normal force coming upwards at an angle perpendicular to the ramp. And we also have tension moving in the direction of that rope. Okay, this time we've got gravity pulling it downward. We've got a normal force. This normal force is pushing it this way. And this wall is pushing it that way. Remember, they're always perpendicular to the wall. Okay, a few more examples on the second page. An object being pulled by a force parallel to the surface. Okay, so we definitely got gravity. We've definitely got the normal force. And we've also got this new force pulling it. Now they don't mention whether it's at a constant velocity or not, so they don't mention whether there is or isn't friction. Maybe you can assume there's friction. Maybe those are balanced, right? If it's being pulled at a constant velocity, you know friction has to equal the pulling force, but if it's not, if it's speeding up to the right, then you know friction is going to be smaller. In this case, it's at an angle, so you still have gravity downward. You have this angle coming up to the right of force, but you also have a little bit of normal force pulling it upward as well. Okay, and then again, maybe, most likely, some friction. Okay, the force is going downward, but the pulley is changing the direction of that force. So by the time that force gets to the box, that gravity downward, the tension of the rope is pulling the box upward. Okay. Here we've got gravity pushing it downward. We got a force that also pushes down leftward. And then we've got an upward normal force, and we've got a little bit of friction to our left. Okay, object is following no air resistance, which means we've got gravity, and that's it. There's no air resistance. Okay, in this case, the object is falling at a constant velocity, terminal velocity. The only way that would happen is if our forces were balanced. So we definitely have gravity coming downward. We need some other force going upward. Since it's in air and it's reached terminal velocity, that must be the friction from the air. Okay, ball's rising in a parabolic trajectory. This is kind of a trick question because it's in the middle of the air, and so the force that you exerted to throw it up in the air is no longer in contact with it. So you still have gravity downward, and that's it. You may say, well, it's moving this way, so it's going to have a little bit of friction from the air pushing it that way, but that's a really small amount of friction compared to the gravity. Okay, top of the parabolic trajectory, again, same thing. You've got gravity downward, and there's no other force pushing on it. Maybe there's a little bit of air kind of pushing it in the opposite of motion. If it's at the top, that means it's going back down, so that means it's moving only to the right at this point. So you have a tiny bit of friction to the left. Okay, but in all reality, you could probably ignore those two frictions because unless we specifically state it, we usually do ignore air resistance because it's so small compared to everything else, unless you're moving really fast or you're really big. Okay, so that is how you do force diagrams. So good luck and happy physicsing.